Welcome to Think Global Education Services. Today's topic is electric field, potential, and force. So let us take a charge. It could be a plus charge, minus charge. It could be electron, proton, or any other charges. Let's take a charge and let's consider that as a point charge. Point charge means all the charge, that is the quantity charge, is accumulated at a particular point. Let's say this is the charge, and we can name the charge as Q. Now, as we have learned, as we know that like charges mean charges with the same charges which are similar. For example, protons and photons. They are called as like charges. Like charges repel each other, similar to that of a magnet. In magnets, like poles repel. So likewise, like charges repel each other, and unlike charges will attract each other. For example, a proton and an electron. Now here we have a charge Q. It could be a positive charge or a negative charge. So let us consider a region around the charge. Region means space. So this is the space around the charge. So you can put the charge in the middle of the circle. So here, the circle is the space around the charge, and the charge is here at the center. Now, what I'm going to observe is I'm going to do an experiment in which this is the charge which is kept, and I'm going to draw a circle around the charge, and I have another charge with me here, and when I keep this charge at a distance away from this charge, let us say this is the distance R1. At a distance R1, this charge does not feel any force due to the charge Q. Let's name the charges as Q1 and Q2. So Q2 does not feel any force due to Q1. Now, if I move the charge Q2 inside the circle, then the Q2 is moving inwards. So I did not move the Q2 now. Now the Q2, I move the Q2 inside the circle. That's the work I'm doing. So I place it here at this position. Let us say the position is A, and I leave it there. So after some time, I see that the Q2 has moved here by itself. So what has happened is that the Q2 has experienced a force of attraction from Q1 and is moving towards Q1. It is similar to that of a magnet. That is what I can expect is that if you take a magnet here, and this is a magnet, let's assume this is a magnet. So here's the North Pole and this is the South Pole. And at a distance away from, let us say the distance is 1 meter between these two magnets. These are very small magnets, so the force of attraction or repulsion will be very less. So you can consider it like that. They're not strong, they're weak magnets. So let's say mildly strong magnets. So here's North Pole and South Pole, this small magnets. So now when they are separated by a distance of 1 meter, there is no force between them. Now in case if I brought this magnet nearer, then what I can expect is, since I'm bringing the North and North Pole together, that is North and North Pole together, so what I can expect is I can expect a force of repulsion. So likewise, here's a region around the charge. So when I bring the charge into a region around the charge feels a force. So now I can name this region as the electric field. Since it's a space, that's why I'm calling it as a field. So, and the force felt by the charge is called as the electric force. So when I bring the charge into the field, it feels a force. So the first thing we can say is that the force felt by the charge Q2 is proportional to the two charges, Q1 and Q2. That is one aspect of knowing, that is one aspect of understanding the force. Another aspect is that the force must be proportional to E, the electric field. And here E represents the electric field. So I can write that as electric field. So what would be the force here? Force is equal to the electric field divided by the electric field due to Q1. Since this is the force felt by Q2, force felt by Q2 is due to Q1. So electric field divided by Q1. So what I can say is that force felt by Q2 is equal to E multiplied by Q1. That is the electric field due to Q1 multiplied by Q2. That is the force felt by Q2. That is electric field due to Q1 multiplied by Q2. Rather than writing it as Q1 and Q2, we can write it as generalize it as F and Q. That is, what we can say is that F, the force, is equal to electric field multiplied by the charge. And the electric field is force divided by charge, Q. Yes, so this is the right representation. So now what we can do is that now we have to learn about potential. So potential is nothing but it is energy. So I told you that when I bring the charge to point A, the charge feels a force and it moves to point B. The question is, I did not move the charge, but the charge moved itself. So where did the charge get the energy from? Because in order to move, the charge needs some energy. So it received that energy by virtue of its position in relation to the charge Q1. So what I can expect is that I can expect an energy is distributed in this field, and due to its position within the field, the charge Q2 gets the energy from the field and converts the energy into kinetic energy so that it can move. Either it can move into the charge, that is, it can move into the electric field when it is attracted, or away from the charge Q1 when it is repelled. So that's how it receives that energy, and the energy it receives is called as the potential. So what we can do is that we can represent it in a different way. That is, we can represent the potentials as concentric circles around the charge. For instance, let's say this is the electric field due to a charge which is at the center here, middle. Let's put the charge in the center, Q. So I can expect that the potential around the charge when at a region nearer to the charge is V1, and the potential here is V2, and the potential here is V3, and so on. So what I can expect is that, so if I play the charge, let us Q, the charge is the symbol. So here is the plus Q charge. Now here I bring another plus Q charge to this position, that is position V3. So the potential along this concentric circle V3 is the same. That is, if I place it here, there is V3, and if I place it here, also V3, and here is also V3. So now I place the plus Q charge at the potential of V3. Now there will be repulsion. So what will happen is that it will travel to a new potential. Let's say this is V5. So it has taken some energy from V3 and it has gone to V5. And that's how we can represent the electric potential. So electric potential is represented by the letter V, and its unit is volt. And sometimes you can call that as the potential difference and voltage. So it all means the same, but they have different connotations, but meaning is the same. Somehow the charge gets the energy from the field, and that energy is called as the potential energy of that is received from the field. Now, as we discussed, the charge gains the potential energy and moves to a new position within the electric field. So the relationship between electric field, or here, instead of writing it as saying it as electric field, we can say that the electric field strength, it means the same. Electric field and electric field strength, it means the same. So here, that it as the relationship between electric field and the potential is E is equal to V divided by the distance the charge moved. So E is equal to V divided by D. That is the relationship between electric potential and electric field strength. So now we have three equations which relate electric field with the force. Now here, instead of E, we can write V divided by D multiplied by Q. This is also force. Now in other words, we can represent V in terms of energy. So here V is equal to the energy divided by charge. That is energy transferred by charge or energy taken per charge, that is also V. And in another way, we can also represent the force using Coulomb's law. So that we can discuss in another videos. Now here we can only discuss about the electric field, potential, and force, how the three quantities are related. Here the force is the electric force, and the potential is electric potential, and the field is a space around the charge in which, if we introduced another charge, it will feel a force due to the first charge. This when we have here the charge is here, the field is due to Q plus Q, and the second plus Q, that is, we can take that as Q2. The Q2 plus Q2 experiences a repulsive force due to the repulsion force due to the field of Q1. It is similar to that of magnetism. In magnetism, what we have is that we have magnetic fields. When one magnet is introduced into the field of the other magnet, it feels a force. It can be repulsion or attraction. It is very similar to the magnetic field. The electric field is similar to the magnetic field, but there are simple differences between electric and magnetic field. For instance, a moving charge, or if there is an electric field, there can be a magnetic field associated with it. That's where electromagnetism comes from. So, for instance, let us say, so how the interaction between electric and magnetic field will appear. So we can discuss about that. The interaction between the electric and magnetic fields. In case if you have a magnet and I have a current carrying wire near to the magnet. So what will happen to the current carrying wire is that it will feel a force due to the magnetic field. That is, here is a magnet and here is a wire in which there is a current which is going in this direction, and so this is the north and south pole of the magnet. So we can expect the field to be like this. The field from the magnet goes from the north to the south pole. So here you can expect that the electrons which are moving inside this wire will feel a force, and that force will be a deflecting force. That is, they will change the path the electrons are moving, most probably perpendicular to each other. So like that's how the force will act. It will change the path of the electron. So that we can learn during magnetism, when we learn about electromagnetism. Right now, we can learn how the electricity or electric field operates. Now, and then other important fact about the electric field is that how the electric field is oriented in space. Let us say here we have a plus Q charge, and here you have minus Q charge. The electric field will be, let us say this is the plus Q, we can represent it as a circle, and here is another minus Q. These are charges, point charges. So the electric field will go from plus Q, so we'll go from plus Q to minus Q. And it will since these are point charges, it will go in all the directions. So like this, and it will go from all the directions. We end up at minus Q. And if I have only one charge, then let's say this is plus Q, then I can expect radial fields, that is outwards in all the directions. So the lines which I'm drawing here are called as the field lines, electric field lines. and this is the minus q, and I can expect all the electric field lines to come inside into minus q. So they are all the electric field lines will not intersect with each other. That's the other point. So I have to draw it in such a way that they do not intersect with each other. So I have to draw it using straight lines like this. As straight as possible. So here I don't have a ruler here. So you have to draw it straight. Let's assume they are straight. And they're all coming in. I have to put, let's say this is minus q charge. So now I can also draw a region. So I drew a region around the charge that is inside the magnetic field, inside the electric field as potential. That is the concentric circles. So here I can draw the concentric circles with the field lines and the potential, which I'm drawing here as circles, dotted circles. So I can use another color to draw the dotted circles to make it clear. Let's draw it here. Here, as you can see, I'm drawing dotted circles. So these dotted circles represents the potential, and the potentials are always perpendicular, are drawn perpendicular to the electric field lines. And as you can see, these potentials, the concentric circles, are called as equipotentials. That means the potential along this circle, this dotted circle, the first circle is the same, but it is different from the second circle, and different from third, fourth, etc. So each and every single circle, the blue circle, are called as the equipotentials around the charge, equipotentials, and the red lines which are going out and coming in to the charges are called as the electric field lines. And different charges, that is, when you have charges, many charges together, the electric field lines will move around the space between the charges, and it will go from plus q to minus q. And when you bring another charge into the electric field of one charge, there will be force between the two charges. It can be either be attractive or repulsive forces. And we had formulas which related the force with the electric field and electric field strength to the electric potential. And thank you for watching.